Hi everyone, and welcome to MAFAT Radar Challenge online meetup. This is a meetup of our competition, a data science competition in which we ask participants to help us distinguish between humans and animals in radar tags. My name is Idan. I'm the VP product of Webix, the company that helped MAFAT organize this challenge. And let's go through the agenda for today. First up will be Sefi. Sefi is the winner of, is the representative of the winning team in the first MAFAT challenge, and he will share his general insight about his personal experience of participating in data science competition in general, and also will present some technical aspects of his winning solution. Then we're going to have Tom, which is our radar expert, and he will provide we'll try to provide you with some common knowledge in radar data signal processing, while also explaining the competition data specifics in detail. And then later on, we're going to have Erez, which is our radar challenge team leader. He will conclude the meetup by going through the competition details in full, starting from the registration process, the evaluation metric, the Codala platform, and any other information that you would like to get about the competition. Just for everyone to be calmer, you can watch this recording later on. We will make it available in the competition website, and you can feel free to ask any question you have in the YouTube chat box. And each presenter will try to save some time in order to give you the best possible answers during his presentation. So first up is Sefi.
Thank you, Idan, and thank you for having me. So as Idan said, I'm Sefi Cohen from Ben-Gurion University, and I'm super honored to be here and to share with you our solution for the last MAFAT challenge on behalf of my team. So just a second. So a couple of words about the team. We're 6 data scientists. Yoel, Amiel, and I are from Ben-Gurion University, and Oad Mossi from Bar Ilan University, Itai Aran from the Hebrew University, and Philip Tanner from Deep Checks. And as you can see, it's not the first ML competition we participated in, and I truly believe in ML competitions because I think it's taking me out of my comfort zone, and I can tell you from my experience that I learned from every single competition I participated in. For example, in this competition, that was the first time I dealt with aerial photos, and I learned a lot about convolutional neural networks and augmentation techniques. And about this challenge, we've got thousands of aerial photos with bounded box vehicles on the photos, and we had to classify the size of the vehicles, the type of the vehicles, the color of the vehicles, and we had to identify if there is any objects on the vehicles like sunroofs, spare wheel, or something like that. And the evaluation metric was mean average precision, and it was multi-class and multi-label challenge. And our solution, as always, I have to say, based on extremely massive ensemble of models, and we did it according to the 3 building blocks of ensemble methods. Our base algorithm was CNN convolutional neural networks, and we generate the diversity using different resolutions, different color systems, and augmentation techniques. And we enforced the diversity using ensemble selection technique inspired by the AAAR. The AAAR, it's a technique that I developed almost 5 years ago with Professor Lior Rokach from Ben-Gurion University. And the main idea of this method was to generate a variety of models, and then to pick the high performance models, to cluster them, and to pick the most accurate model from the validation set in each cluster, and then to combine them together. And in that way, we got super diverse and super accurate subset of models for our ensemble systems. And our base algorithms, our CNN architecture was ResNet, Inception, MobileNet, VGG, 16, NASNet Mobile, NASNet Large, Exception, and DenseNet. And as I said, we generated more data sets with different resolutions and with RGB color system, HSV, and grayscale color. Then we trained the model using different augmentation technique, include flipping, rotating, shifting, and zooming. And one of the interesting augmentation technique we used was just flipping the RGB channels. And in this example, you can see what happened when we flip between red and blue, the red and the blue channels. We got the same car, but with a different color. So of course, in that case, we had to change also the labels, because it's one of the labels that we need to classify. And all these models and all this diversity provide us huge repository of models. Then we combined the model with ranking average. The idea of ranking average, it's just to take all the probabilities and to normalize them together to ranks. Think about that. We got prediction from different architecture and different color systems. So the probabilities came from different distributions, and in that transformation, we transformed them into ranks, and then we normalize them and combine them together with just regular average. So to wrap up, what we actually did, we download the data, we generated more data sets based on different color systems, different resolutions, and we trained the model with different augmentation methods, actually regular augmentation methods, except the flipping color that was something unique. And then we normalize them and average them, and actually that's all. In the bottom line, we reached the first place on the private leaderboard, but in the public leaderboard we took only the third place. But I think that actually the ensemble method, with that ensemble method, we provide robust model that the hype in the private leaderboard. And what we didn't try was custom augmentation. And I can tell you that today I'm investigating this field in my PhD, and I'm pretty sure that custom augmentation could boost our results even more. But that was almost 2 years ago. This challenge was almost 2 years ago, and today I definitely think that TTA could give us more. We didn't use the entire information about the real image. we just learned from train the model with the cropped vehicles, and we used only convolutional neural networks. We didn't use classical computer vision or classical machine learning algorithms like XGBoost, KNN, or something like that. We didn't try self-supervised or semi-supervised approaches, and in that case, something like half of the data was unlabeled. So I believe that a semi-supervised approach or self-supervised approach could achieve better results. And as I present, we just averaged the model, and we didn't try more sophisticated combiners like stacking or something like that. And I can say that my primary takeaway from this competition is if we did it, everyone could do it, because actually we joined to the competition just in the middle of the competition, and all of us are super busy. All of us in full-time jobs, and most of us are students, and most of us are parents, and we did it in our spare time. And without computing power, we just used my PC, my tiny PC with DGX 1080. And I believe that we did it by a great teamwork. And more details about our teamwork could be found on Philip's blog. He wrote it, I think, maybe 1 year ago, something like that. And we just submitted our paper to ICPR, and I hope to share the paper with you as soon as possible. And I'm here for your questions, if you have. Thank you.
Well, Steffi, maybe I will try and take some questions from the chat box. Idan Tobis asked, did you also flip the HSV?
So, no, we didn't flip the HSV. We just flipped the RGB, and we changed the labels according to the RGB flipping.
Okay, thanks.
With HSV and grayscale, we used the regular augmentation, like flipping, zooming, etc.
Okay, another question from Daniel Khan. Can you elaborate a bit on test time augmentation? Is it like augment a data point, an image, with augmentation during test and then predict?
Yes, actually, what you need to do when you want to evaluate the test time augmentation, you need to augment the test data and then to average the test data. That's all. And in most of the cases, it's increased the accuracy like a magic. I can tell you that I tried almost 20 data sets on my research, and except one of them, except the SVHN, that it's some data set close to MNIST, it's always get better results.
Okay, thank you very much, Safi. I don't see any more questions. So if anyone has any other questions, you can just try write them quickly. And if we don't get any new questions, then we'll go to. Okay, we have some new questions. One of them from Ofek. How did you deal with the imbalanced data?
Okay, so actually we didn't dealt with the unbalanced data. Oh, sorry. I think we used the focal loss to do that, but that's all.
Okay, and another one, Daniel Khan has a follow-up question. So he asks, so it's the same augmentation as in the training then average, then predict?
Exactly.
Okay, perfect. And another question about teamwork management. Did each one of you test a different neural network?
Sorry, again?
Did each one of you test a different NN neural network?
No, we did it all on my PC. So thought about the right architecture, why, and that's all. But we did it together.
Okay. Thanks, Efi. There's another question by Gal. Can you talk a bit about task allocation and time management when working in a team?
Okay, so actually, I can tell you that I worked on it only in the morning between 5 a.m. to 6 a.m. because it's the only time, it's the only spot of time the only spot of the day that I have the time and I have I can focus on it. So I worked at between 5 to 6. I know that Yoel and Amiel worked in the evening, but we try to put or to schedule a couple of meeting and to synchronize.
Okay, thank you. Any other questions? If you have them, so now is the time. Okay, so I think we're about done. Thank you very much, Efi.
Thank you very much.
Thanks for this fascinating presentation. And coming up next is, just a second, it's Tom. And as I said, Tom is our radar data expert and will provide us with some common knowledge in radar data signal processing, while also explaining the competition data specifics in detail. So go ahead, Tom.
Hi. Okay. All right. So my name is Tom. I'm a member of the MAFAT Radar Challenge team, and I'll be here to talk about some of the important things you have to know about radars before you delve into your deep neural networks. So I'm really excited that we have this competition because radars have been for a long time. They've been for much more than 100 years. As you can see, they filed a patent. Someone filed a patent in 1905 in Germany for radar, and so you can see it in the middle here. Then we have radar in World War II for tracking, for locating airplanes. And so it is used in the aviation, in defense, security, and also in the automotive industry. Now, as you know, cars do have radars. And recently I found out that also cell phones have radars. So the key advantage of a radar is you can detect things far away and in all weather, night and day. All right, so a lot of focus have been dealt in detection. As you can see, we have here an old radar. It's a phosphor, and it just shows a blip if there's a target, but not much more than that. Later on came tracking. The operator could see where the target has been. It could, while the target is being tracked, it can know its speed. But not much more than that. So there is a classification gap So there's a limitation of what you can tell from a radar signal. For example, you can't tell the difference between a jet plane and a corporate jet. That'll be hard to tell the difference just by looking at the simple radar returns. So let's talk about something more interesting to us. This is ground surveillance radars. And in ground surveillance, we're looking at, we want to detect moving objects on the ground. Some of the legitimate targets are vehicles, people, animals. It's ground animals, but also low flying birds. Along with that, there's clutter. It's noise, something that we don't really want. It's vegetation, swaying in the wind. We don't really want those in our detection, but they do come up. So target classification, it can be done easily for vehicles. So if you want to distinguish, for example, between vehicles and birds, they move relatively fast, but the difference between those is the size. So this is a factor which we can actually use to classify. Trees and vegetation sway back and forth, and they have a unique signature, so we can tell what is a tree or a. So the really hard question is that we're left with is telling the difference, and the interesting question is telling the difference between a man and a mammal, or a human and a mammal. Let's be more general. The problem is that they have similar size, the similar motion speed, and similar motion type. They actually have, humans have 4 legs, mammals have 4 legs, humans have 2 legs and 2 hands. So it's kind of hard to distinguish between the two. So you can ask yourself, why not use cameras? So cameras have been used, and we use cameras. They're complementary solution. The radar can tell the operator where to look. The operator can look in that direction, try to find on the ground what the target, and try to classify if it's a man or a mammal. But there are limitations, and there are some key disadvantages why cameras can be used all the time. As you can see, I have here a picture of a fog, so it's hard to tell what's going on behind the fog or in the fog. Cameras have a limited range. The field of view is narrow, so you can't see the whole field of view. And bad weather is also hinders your capabilities. So there have been attempts to try to classify human animal, but the current performance is not market standard. So that is why we're going with this competition and trying to improve the results. There have been used signal processing, statistical data modeling to try to figure out if it's man or mammal, but once again, it's limited results. So in this challenge, we explore new ways which you can help us determine whether it's we have a human or a mammal. We provide unique real-world data. It's the quality is really high, and this is actually the first time that I've seen it around in the internet. So I'm excited that it's finally happening. and a lot of groups and people can help with this problem. We hope that you use different and advanced machine learning strategies, including neural networks. So the theory about radars is this. We have a radar with an antenna. The antenna transmits a signal, an electromagnetic signal, onto targets. So this is our target. It's a man walking. Behind him, there's a tree. The transmitted signal bounces off the person and then comes back again to the antenna, the radar's antenna. But notice that there is a Doppler shift. This is a physical phenomenon which happens. And if the person is coming towards the radar, then the Doppler shift is positive. If the person moves away from the radar, then it's negative shift. It's a linear proportion to the velocity of the person. So the next thing to talk about, if we talk about Doppler, the Doppler phenomenon, is talk about what is microdoppler. So microdoppler is a technical term which we use when we're talking about motion within a target. So a target may exhibit, for example, if we talk about a car has wheels, the wheels move. Also the whole body moves, but also there is a wheel movement. And the wheel movement can generate Doppler, a certain Doppler pattern, along with the main body that's moving. If we talk about a person or an animal, its hands and legs move also with the body, but the body is not totally detached, and you can actually see in the Doppler the movement of the hands and legs. Also, trees move, they sway, and their branches, you can actually get Doppler movement from the branches of trees. All right, okay, this is complicated. So let's go and talk about how do we view the Doppler. So let's start out with where we emit an electromagnetic wave. We get radar returns, and we can actually look at the spectrum of of the signal that came back. We're talking about in the x-axis, we're talking about Doppler bin or frequency, and then the y-axis we usually talk about power, represented in dB or log power. In this example, we can see an animal that's walking, and we can see the peak here that's related to the animal. There's also a peak here towards the 0. This is, I can tell you, this is clutter. This is something that we don't want, but it's vegetation. We don't know what it is. It could be bush, it could be a tree. We don't know. And in this part, we have noise. Okay, that also doesn't interest us. What interests us is the animal, actually. So this is one snapshot. All right, this is a vector with one snapshot. But if I take the 32 snapshots, put them together side by side, I can actually get something that's called a spectrogram, and that's another representation of Doppler. And we can actually see with our eyes the movement of the animal. So this peak of the animal maps to around the Doppler bin 38, and you can see the animal walking. You can see the signal. This is a heat map of the animal walking. The peak is the animal, and you can see that there's well, you can if you try to look and peer into it, you can actually see some movement around this around the main or the peak, which actually tells you this is limb motion, the limb motion of the animal. If we look around the zero Doppler bin of the spectrogram, you can actually see this is the vegetation. This is the part that less interests us, but it exists and you should know it exists. All right, let's continue. So real world radar data is noisy. So the radar sends signals, and the total returns of the signals is a desired object, but there's undesired noise. There's vegetation, as we talked about. There's internal electronic noise from the radar itself. There's external noise also. All right, so I'm going to show just some other spectrograms of, this is a spectrogram of an animal. So we are pointing here at the animal movement. This is along about, I think maybe it's more than 32 time steps, but I mean, what will interest you is 32 time steps. This is the basic frame. The spikes here, the spikes along around the main, the peak is the limbs moving, and we've talked about that. Also around the zero, we have zero here. Also, you should know that zero is around the top part. It's on the top and bottom. This is like Pac-Man. It's around 0 meter per second. So you should know this is vegetation, as we talked about. Let's continue and see how a person would look like. So, well, this seems like the person here is, you'd see the limbs moving really good, I think. Along the center of the body mass movement, you can see the movement of the limbs, and so, but you should know also that in this image there is vegetation, clutter, and the person is moving really close in the speed of the clutter. So you're getting clutter plus the person itself. Be aware of that. Okay, so how do we get a spectrogram? We provide you with raw data, and the raw data is segmented. It's matrices the size of 32 by 128. This is 32 time steps by 128 raw data time samples. The samples are complex INQ values of the voltage of the received signal to the radar. I is the real part, Q is imaginary. So in order to convert the raw data to a spectrogram, we provide you with a script, and let's just go over what's being done there. First of all, we subtract the mean out of each vector, out of each snapshot. We multiply each element-wise of the 128 samples by a hand window, okay, or a taper. You might have heard the word. This is to decrease frequency side lobes. It makes the image a bit better. All right, then we apply an FFT along the 128 points. This is the y-axis. We apply the FFT on the y-axis, not the x-axis. And then we take the log of the absolute value of each cell. So this is like the log power. And then we have a stage where we just put a threshold, and then with a median, and then we just can display the image and see what we've got. All right, so let's talk a bit about the data variety, and the metadata that we provide. There's a training set, and there's an auxiliary data set, and there's a test set. The training set will provide you with a track ID. So we have a target that we know we're looking at, and we're tracking it by our sensor, a radar, and we give it a track ID. So each frame will contain, along with it, track ID in the training and auxiliary. Okay, I'll repeat that, in the training and auxiliary only. There's also location information. It's only, you'll only get like a number. You won't really know where geographically it's located. There's also geographical type. We just say what terrain it is, also without too much details. There's a radar ID, a sensor ID. There's a label with a day, and it's labeled if it's human or animal. So visually, we can actually, we can see here that we have a map. So we give you a geolocation. We have a sensor. Here is a single sensor per location, per this location. And it could be in multiple days or a single day. There's a track. We split the track into segments. These segments are your frames, and you'll tell us what's in the frame on the testing set. Also, you should know that in some locations there are more than one radar, and vice versa. Also, we've recorded in different days, so you won't get like just a single day per sensor. All right. And in the testing, so in the testing set, you'll only get the segment ID, which we want you to tell us what's the label, what label you think there is, you see in it. We also provide raw data matrix. This is for all our data. There's we include the Doppler center mass. So we tell you for each segment, in each snapshot, where we have tracked the target, and this is the center of mass of the target, Doppler-wise. We also provide a number called the SNR. So this is a signal to noise ratio. We tell you if the signal was high or low. Okay, and we'll talk about this in more details in a couple of seconds. So in total, we have a training set of 6,656 segments. The test set is 106 segments. And there's something we call an auxiliary data set, which contains segments with synthetic low SNR, signal to noise ratio. So we took high signal to noise ratio target. Both. Yeah, both, actually, human and mammals. And we added to it noise, therefore decreasing the signal-to-noise ratio. There's a data set in the auxiliary data set which is background only. So so we've taken the recordings of where targets walked, and right next to it or close by, we gave you the data of how the background looks like without the target. So this should be interesting for you. There are also controlled experiments of just humans walking in a very particular way. This is on the auxiliary data set. On the training set, they just walk however they want to. But in the auxiliary data set, we have a real true controlled experiments of humans walking. So all of these won't appear in the test set. All right, so you don't have to study the background. I mean, you could make your own signal to noise ratio, whatever you want with the test set, but it's not, we don't add noise to our test set. I mean, there is no controlled experiments of humans in the test set. The test set is actually more randomized frames, you should know, as opposed to the training set, where the training set, the tracks are almost sequential. So a single, you can track a target. You can actually lay out the segments one by one and piece it together to get a bigger picture of how it looks, of how the whole experiment look. But in the test set, you can't do that because it's randomized. Well, you can try to, but it's hard. What you should pay attention here as you do the learning part is beware of track correlation. Also, there's a problem with overstudying your data. We don't want you just to memorize the data. You'll probably get bad results. Don't overstudy the background, all right? So, I mean, there have been tries, people have failed just studying just the background and not the target itself. And yes, and try not to ever overfit your models. All right. Okay, so this is the end. We'll try to take some questions.
Yeah, Tom, we got about 15 minutes just for Q&A, and we got lots of interesting questions in the chat box. So just feel free to pick the most relevant questions, and if you need my help, then just take it.
Okay. So there's a question here. What's the difference between clutter and noise? Is that clutter explainable? So noise, yes, it doesn't come from the environment. This is when we say noise, it is thermal noise, just generated internally by the radar. Okay. Okay, clutter and animal DB looks exactly the same. Can you explain the difference? All right. The difference is in the dynamics and not the power. So it turns out, as we said, that both targets are about the same size. So the return is just about the same power. So I guess it won't help you much looking at the power. Are the data samples continuous? Yes, so the answer is yes, only for the training, only for training. Okay, is the center of mass an average or a vector the size of the x-axis? So it's a vector. It's a vector. Okay, are there any other problems? Let's see. Does it test?
Maybe Dan has.
Does the test have a similar statistics? The test has the background. So does the test set have a similar statistics of the background? Well, so it's different. It's different. It could be a different sensor. So in a different location, the background could look different. But we don't have in the test set. There aren't. It's not just background. It's the target. All right, target plus you'll get clutter for free. How do you calculate the object center of mass, the white dots? Well, okay, this is our field, and this is just tracking. How many types, I guess, of radars? So you can actually, there's sensors, there's sensor ID. You can just look and count it for yourself.
No, track is divided to segments.
All right. So is a segment ID equal to track ID? So no, we take a track ID and we divide it into segments. So the question is, when you say different sensors, do you mean different specs or different locations? Both.
You answered that already.
Where the Doppler center of mass data came from, I guess we answered that before. We just track. Question 1, does the struct contains the radar parameters? So no, you don't get the radar parameters. You get the frames value, raw data value.
Track correlation. Yes, high correlation.
Wait. Question 1, tracker correlation. This is actually a tracker level phenomenon. Does your tracker deal with that to an extent, or should we expect high correlation? So there's high correlation.
Yes, David comment.
Just to make sure, we've got 128 by 32 samples. Are the 4,096 samples are continuous? Yes. Is there only one human animal in each segment?
Except for passing.
All right, there might be passing targets. I mean, that could happen. We can't control everything in the world. Sorry.
Tom, we're getting a few questions about is there only one human or one animal in each segment?
Yes. So as I've answered, it could be more. I mean, usually there's one. There could be more, but this is very rare.
Yeah.
For a short period, it could happen.
I think so.
Some of the Chinese spoken images from the examples.
Not going to get into specs.
Okay, so I see many questions about the specs of the radar. I think this is not the scope of the talk. Duration. Also, the duration is not in the scope. I've seen question about the duration. Why don't you score for the test sets? In the segment. Okay, so in the segment, someone's asking, can there be an animal and the human, both? So no, it's either human or animal, and that's why we label it. Okay, look at that. Well-studied phenomenon. Depends on physical hunch. What's the wavelength?
Outliers maybe 1%, not more than that.
Okay, do you think there could be an outlier in the data? There could be, let's say 1%, not more than that.
Okay.
Okay. Let's see if there are any more questions that we can answer. The example is okay.
Is the center of mass given for the test set? Yes.
Yeah. Okay. So is the center of mass given for the test set? Yes, we give that out. Okay. Fits nearly opposite forward backward. Can you show how that looks like? We can show.
Okay.
Okay. Yeah. So someone's asking. You've mentioned that movement affects linearly opposite forward, backward. Can you show us an example of how it looks? So I think we have here a spectrogram of a person. So this is negative. So the person is walking away from us, and we have here an animal. This is positive, so it's coming close to us. That's it. So plants, why? So in regards to plants, why would there be any Doppler shift? So you're right. Plants do not move, so they're centered around the zero. All right, but they do sway back and forth. That's why we do see them in positive and the negative side. And that's it. That's why they're always on the zero. Although there are some moving plants in the deserts. Right. Well, they were capture data road. For curiosity, could you help with the environment where you capture data? e.g. rock or backyard. So this is just open space. This is nature at its best. Okay, how can you tell if it's a positive or negative Doppler based on a spectrogram image? So on the bottom, you'll usually get the 0, and if you walk up, then it's positive. If you walk down, then you just go like a Pac-Man to the top. That's negative. All right. Preprocessors, maximum HRQ. Let's measure from the following pre-processing step. Sets maximum value of each. In play, okay, place them where there are more than one. They interfere with each other. Okay. Include segments with Doppler acuity. So do the examples include segments with Doppler ambiguity? The targets are very slow. No, we don't expect any ambiguity in Doppler.
Tom, we're going to spend another 3 minutes just taking like the top 3 or 4 questions, and then we're going to move on to Erez's presentation. So you can just pick like the top 3 most interesting questions.
Okay. The script that converts the data to spectrogram, is it verbal that you had in the slides, or is there a version of code, Python? So there is a version of code. Are there only 2 directions of the target movement? Change of direction motion. The change of direction also possible. Observation. What happens in the movement? The objects on the side. Okay. So are there only 2 directions of the target movement? Question number 1. Well, the radar can detect only forward-backward movement. Is a change of direction also Is a change of direction also possible in observations?
Yes.
Yes. Yeah, let's see if there's more questions. Give some more details about the performance of human operators analyzing these spectrograms. Could you give some details about the performance of human operators analyzing these spectrograms? Well, obviously I can't, I don't know. Haven't met anyone.
Use cameras.
But if you use cameras, you can achieve really good results. For moving, non-moving part. Non-moving part. So how can I visualize microdoppler for moving and non-moving parts? When a person walks, there's a main, the main body, the abdomen, and that is the center of mass. You should notice, and it's on the, you can see the main return, the high values from the body, but alongside it, there are the movements of limbs. All right. Okay, that'll be it for today. Thank you very much for joining us.
Thank you very much, Tom, and it was really interesting, and you can see by the number of questions that everybody is really fascinated by the subject. So just for everyone, I know that there's many questions that still left unanswered, and we're going to try to pick them all up and provide answers within the competition website, within the competition forum, and we will create a thread with questions to most popular questions that was raised in this presentation. And once again, thanks Tom for this presentation. And next up is Erez, which is the MAFAT Radar Challenge leader. And he's going to conclude the meetup by going through all of the competition details, competition in full, starting from how to register, what is the evaluation metrics, the datasets description, and many more subjects. And the same as in the other presentations, feel free to ask questions in the chat box, and Erez will leave some spare time in order to answer all of the questions. So thank you, and you can take it as.
Okay, hello everyone. Good evening. I know there is a lot of questions unanswered from the previous session. Please feel free to ask us the question in the forum and we will answer it. So MAFAT challenge. FAST challenge is basically a series of competition. We had computer vision about 2 years ago. Since then, we worked very hard to get to this time with the radar competition. So the competition, as you probably understand, focused on radar signals. And as you can see here, we have more interesting competition to come. We're working very hard to give you high rate of competition. A quick overview on the competition timeline. So we launched a competition on the 15th of July, and you have until the 8th of October to work on the public data set. In the 8th of October, we will publish the public data set labels, and you will have 1 week until the competition ends, and only 2 submissions to private data set. The prizes, as you can see, so the third place wins $5,000, the second place wins $10,000, and the first place wins $25,000. A very high note from our side: you need to accurately classify human or animal from different types of radars and different types of fields. Make sure you do this and you're not overfitting one radar or one specific area. So you had the overview of the radars by our radar by Tom. You also wanted to see some animals and humans spectrograms. Just don't be very specific with the spectrograms, because when radars first invented, people actually sat and heard the noises of the radar, and maybe this is a kind of lead that you can thought about and not go to the let's say more trivial method to do computer vision or something like this. As you probably understand, labeling a human or an animal is a difficult task because they have a similar movement in this space. So focusing on the stages of a competition. So as I described earlier, we have 2-stage competition. In the first stage, the public phase, you will get the training set and the public test. Afterwards, you will get the private test labels, and the training set will still be with you. And you will give us the private test predictions. About the evaluation, I saw some question earlier about it. So we are using ROC AUC to evaluate your predictions. and each participant are asked to give a probability score for each segment in the provided test set. So basically, you are working on the segments. Terms and conditions. It's very important that you read the terms and conditions in full, and I will emphasize some important issues. We have two stages of the competition. In stage 1, you have 2 submissions per day. In stage 2, which is 1 week long, you have only 2 submissions total. About teams, you're allowed to gathering together in teams. I saw some person who looking for a team, but please make sure you taking into account the total submission amount that is allowed. Basically, you see the formula here, but each person needs to be need to check that you are not give more submissions than allowed, because then you'll be disqualified. If you use external data for your labeling or for any other thing you need, you must make it publicly available until the 15th of September. Afterwards, you will not be allowed to use external data for any reason. Okay, so a quick overview about the dataset structures. As Tom described earlier, you have the geolocations, you have the sensors, you have the tracks, and in tracks getting into segments. You are working on the segments only, and in each stage you will get the CSV files and pickle files that in it you will find each of the fields that Tom described earlier. About the registration process. So we have two tracks that you need to register in it. One is MAFAT challenge website. You need to register here, and then we'll send you immediately the data. In order to participate in the competition and to get access to the Colab notebooks, Python codes that do the conversion, and other notebooks that we built for you, you will need to be a registered member in the Codalab and register to the competition in Codalab site. So I will just do a quick Codalab review. It's basically very simple, but just to get familiar with the platform itself. So here you have the landing page of the Codalab. You have the competition timeline and some basic data about the competition. About the evaluation, as I described earlier, we give you some more detailed method how we evaluate your prediction. Terms and condition, very important. I recommend for everyone to read it in full. A quick overview about the data, what are the data fields that you need to work with. Some resources that we found relevant for this competition, FAQ, and of course, the specific timeline of the competition. In the Participate tab, you get the links to the notebooks, the scripts, and basically it's the same as the Data tab. In the Participate, here you submit your files, and it may take time, so be patient with it. As for now, until the 15th of October, you're allowed to get prediction to stage 1, the public test. And please make sure you do only 2 submissions per day on the public test phase, and the private test phase you have only 2 submissions. So be careful with it. Okay, so here you can see we give the results. There is some captures that we've done for this presentation. And the leaderboard is published every day, and you can see where are you positioning regarding to the public test phase. And on the private test phase, we will not publish until the end of the week. We also have a forum where you can ask questions. We have a team dedicated for this competition, and we will try our best to answer as in the minimum time that we can. And in the team management tab, you can gather a team together, and you can ask joining joining an existing team. So I will do now just a quick overview, troubleshooting. So the procedure of submitting a zip file, make sure you're following these specific steps to submit your file. And of course, the format need to be a CSV as described in the evaluation tab or in FAQ. So the submission results may take time, usually a few minutes, but in rare occasion, it may take a few hours. We're paying attention to this issue. We know the time is critical for you, and we'll try our best to be at the minute size of you. If you have some personal question that you want, you have the email in the website team@mafatchallenge.com, and we'll answer you shortly. So just to conclude everything I described for now, the timeline. So we have until the 15th of September to get some external data if you want. And again, I remind you that you need to make it publicly available. On the 1st of October is the team merger deadline and the competition entry. And afterwards, in the 8th of October, you will get into the private phase. And from this date and until the 15th of October, you have only 2 submissions, so pay attention to this. Besides that, are there any questions? So I will now go to the questions and see if there are any specific question that you ask. Okay.
Yeah, so everyone, now is the time. Any question you have regarding the competition, and we will try to answer it.
So anything, Delcar, you ask how to enter as a team. In the Codala platform, you can build a team and write there all the team members. You ask about highest NR, lowest NR. So basically, it's a signal to noise ratio that the radar get from the target. Per day depends. Yes, so Alon, you asked, does the number of possible submissions per day depends on the number of members in the team? So yes, we give 2 submissions per team member. Okay, so if you are a team, we give 2 submissions per team per day. So this is the formula. Larger team, well, right, it's unfair advantage for larger teams. So larger team are more powerful team than a single person. We are 3 people registers.
Just to clarify Alon's questions, that so each team get 2 submissions per day, the same, even if the team has 2 members or has 15 members, they still get only 2 submissions for the entire team. So actually, there's no unfair advantage for larger teams. They get the same number of submissions.
Okay, so Israel, you ask, what is the competition path that the notebook asks to give after mounting the drive? I don't really understand the question, but basically, if I'm referring to the notebook, so we build notebooks that do conversion in Python to the radar signals. Just me, you ask, why does the number of submissions per day matter? Isn't the quality of a signal submission important thing? So basically, we chose to limit the submission per day to 2. This is the method that we chose to do this competition. Okay, is there any questions left? Okay, so I just want to thank you all for joining this webinar. We are very excited that we get into this phase. As I said earlier, the team is dedicated for each question that may come up during this competition. And please feel free to ask us, to write us, and we will answer everyone specifically. Okay. Thank you all for joining and hope to see you on the leaderboard.